Let's repeat the same thing, but I'm walking a little bit faster. I start to measure the time now. At 5 meters, 3 seconds. At 10 meters, 7 seconds. At 15 meters, 11 seconds. At 20 meters, 15 seconds. At 25 meters, 19 seconds. Let's begin in the coordinate system from the previous video. Let's keep the white line from the slower walk visible. In the same coordinate system, we display the new measurement points for the faster walk in blue. When we fit a pink line to the blue points, we notice that the line is steeper than the white line. We can conclude that the steepness of the line tells us something about the velocity. Let's bring up both measurement tables and compare the time values. For the blue points, we reached 25 meters in 19 seconds, whereas for the red points, we covered the same distance in 32 seconds. That is, in the case of the red points, the measurements took more time to cover the same distance. Thus, we can conclude that for the red points, the uniform motion was slightly slower, whereas for the blue points, the motion was slightly faster, and this is easily observed from the slopes of the lines. The steeper the slope, the greater the velocity. Let's calculate the physical slope of the pink line, which is the velocity. Let's choose 2 points from the pink line and plug these points into the velocity formula. The numerator is the change in position, and the denominator is the change in time. Simplifying the calculation, we obtain a velocity of about 1.4 meters per second. In the previous video, we got the physical slope of the white line as 0.8 meters per second, and now we got the slope of the pink line as 1.4 meters per second. So these numerical values also show that in the latter measurement the walking was slightly faster. Let's zoom in and examine more closely how the slope of the line relates to velocity. In this initial situation, the velocity is 1 meter per second, meaning that every second we move 1 meter in the positive direction. If we steepen the line and reach a situation in which we move 2 meters in the positive direction in 1 second, the velocity becomes 2 meters per second. Next, if we flatten the line, we reach a situation where in 1 second we move 0.5 meters forward in the positive direction. Thus, the steeper the line, the faster the motion. Let's draw another coordinate system on the left, where the y-axis represents velocity instead of position, and the unit of velocity is meters per second. This is the time, velocity coordinate system. Let's study how these two coordinate systems are related. In the position coordinate system, the physical slope of the lines is the velocity. Because the motion is uniform, a horizontal line is drawn in the velocity coordinate system at 1.4 meters per second, and similarly, the line from the position coordinate system corresponds to a horizontal line drawn in the velocity coordinate system at 0.8 meters per second. Next, let's examine how the steepness of the line in the position coordinate system affects the velocity graph on the left. The steeper the line, the greater the velocity. In this situation, we have moved 4 meters forward in 1 second. Thus, in the velocity graph on the left, we see that the horizontal line is at 4 meters per second. Similarly, when the line increases very gently, in this situation we move forward 0.5 meters in 1 second. So a horizontal line is drawn in the velocity coordinate system on the left at 0.5 meters per second. Next, let's investigate the physical interpretation of the area under the curve in the velocity coordinate system. Let's start by solving for displacement using the velocity equation. Displacement is calculated as velocity multiplied by the time change. The velocity is now 1 meter per second, and the time change is the final time t2 minus the initial time t1. This gives us 3 seconds, and when we substitute the velocity and time change into the formula, we get a displacement of 3 meters. So, the interpretation of the area is displacement, which in this case is plus 3 meters, meaning that at the given velocity, over a 3-second interval, the displacement is 3 meters in the positive direction. Let's see how this displacement is represented in the position coordinate system. That is, we move forward 3 seconds, going from the origin, 0 meters, to 3 meters. So, if we calculate the displacement as the final position minus the initial position, we get a displacement of 3 meters, which is the same as the area under the curve in the velocity coordinate system. Next, let's look at the area from a different segment and similarly calculate the displacement from the velocity coordinate system on the left. The time change is now the final time minus the initial time. The final time is 4 seconds and the initial time is 2 seconds. So 4 seconds minus 2 seconds equals 2 seconds. The velocity remains constant. It is 1 meter per second. When we substitute these values into the displacement formula, we get a displacement of 2 meters. This means that at that velocity, over a 2-second interval, the displacement is plus 2 meters. Let's see how the same information is obtained from the right-hand position coordinate system. We start from the point corresponding to 2 seconds and move to the point corresponding to 4 seconds. From the position axis, we see that the displacement can be calculated as the final position, 4 meters, minus the initial position, 2 meters. Thus, the displacement is 2 meters in the positive direction. Let's see, in an animated fashion, how the displacement is shown simultaneously in the right-hand position coordinate system and in the left-hand velocity coordinate system. We see that as the position changes, an area starts to appear in the left-hand coordinate system. In the final situation, we notice that in the position coordinate system, the yellow point has moved from 0 meters to 4 meters over 4 seconds interval, resulting in a displacement of 4 meters. In the left-hand velocity coordinate system, this is seen as the blue shaded area being 4, whose physical interpretation is the displacement, which is plus 4 meters.